hold your hand up in the dark for a moment and look at the empty air between your fingers and the wall. It feels like nothing, like the plain absence of everything. But that emptiness is the largest single thing in the universe, and it is not sitting still. Right now, in that gap, and in every gap like it across the cosmos, new space is quietly being made, and the making is speeding up. Astronomers call whatever drives it dark energy, and it is about 68% of everything that exists. We can measure it to a fraction of a percent, and we still cannot say what it is. Our finest theory predicts its value wrong by more than any prediction has ever been wrong about anything. So tonight, I want to answer one question. Why is this quiet, invisible energy the most disturbing mystery in all of physics? By the end, you will know exactly what the evidence says and exactly what it does not. Before we begin, if questioning reality this slowly is how you like to settle in at night, a like or a subscribe truly helps the channel grow, and it means a great deal to me. Now, let's ease in. Take a slow look around whatever room you happen to be in right now. There are walls, and a floor, and the soft weight of the air. There is your own body, warm and solid, breathing quietly in the dark. Everything you can see and touch and name is made of ordinary matter, the same stuff as the stars, the same stuff as the planets and the oceans, and every living thing that has ever existed. It feels like the whole of reality. It feels like everything, and it is almost nothing at all. When physicists add up the full contents of the universe, the numbers arrive in a form that quietly rearranges how you think about your own existence. Ordinary matter, the atoms that make up you and me and every star in the sky, accounts for only about 4.9% of everything. Another 26.8% is dark matter, an invisible form of mass that we can feel through its gravity but have never directly seen. And the rest, the largest single portion of reality, is something stranger still. About 68.3% of the universe is made of what we call dark energy, 68% of everything, and we cannot name it. Let that proportion settle for a moment, because it is easy to hear a number like that and let it slide past. Everything humanity has ever studied with a telescope or a microscope, every galaxy catalogued, every particle smashed apart in an accelerator, every atom in your hand, all of it together adds up to a thin skin on the surface of the cosmos. The great bulk of what exists is not the shining matter we point our instruments at. It is a smooth, patient, invisible presence that fills all of space and does something no ordinary substance would ever do. It pushes the universe apart. I want to be careful with that phrase, dark energy, because the name is doing something sneaky. It sounds like an answer. It sounds like the label on a jar, as if somewhere on a shelf there sits a sample of the stuff, and we know its properties, the way we know the properties of water or iron. There is no jar. Dark energy is not a discovery of a thing. It is a name we gave to an effect we cannot explain, a placeholder standing in for our own ignorance, and the honest translation of the words dark energy is closer to this. Something is making the universe expand faster and faster, and we have absolutely no idea what it is. That admission would be humbling enough if the mystery were some minor footnote at the edge of physics. It is not a footnote. It is the majority of the universe. Imagine being handed a complete inventory of a house, every brick and beam and nail accounted for, and then being told that 95% of the building is made from materials that appear nowhere in any textbook, materials nobody has ever held. You would not feel that you understood the house. You would feel that you had been living in it without ever really seeing it. That is our situation with the cosmos, and dark energy is the largest part of what we have been missing. Here is where the discomfort begins to sharpen. We are not vaguely aware of dark energy the way you might be vaguely aware of a sound in another room. We have measured its effects with astonishing precision. We can tell you what fraction of the universe it makes up to within a fraction of a percent. We can trace how it has shaped the expansion of space across billions of years. We can write down equations that describe its behavior so well that they predict the arrangement of galaxies across the entire visible sky. By almost any standard, this is a triumph of measurement. And yet, when we ask the simplest possible question, the question a curious child would ask, the question of what the thing actually is, physics falls silent. This is the peculiar shape of the whole subject, and it is worth naming clearly at the start, because it is the shape we will return to again and again tonight. Dark energy sits at the exact point where our knowledge is most precise and our understanding is most empty. We can weigh it. We cannot explain it. We can predict what it does. We cannot say what it is, and the gap between those two things, between how well we can describe it and how completely we fail to comprehend it, is not a small crack. As you will see before the night is over, it is the single largest disagreement between our best theory and the actual universe, in the actual universe, in the entire history of science. Consider what it means that this is even possible. Physics is the discipline that pried open the atom, that predicted the existence of particles decades before anyone found them, that describes the behavior of an electron so accurately the prediction matches the measurement to 12 decimal places. This is not a field that is used to being wrong. And here, on the largest ingredient of the cosmos, it is not merely a little uncertain. It is confronted with something it cannot account for at all, something that makes up most of everything, and that will, in the end, decide the fate of everything. You might reasonably ask why any of this should keep you up at night, or rather, why it should be the thing you drift off to. The answer is that dark energy is not far away. This is the part that people tend to miss. It is tempting to file dark energy under distant astronomy, a problem for cosmologists staring at faraway galaxies, safely irrelevant to the quiet room where you are lying right now. But dark energy is not out there in the way that a distant galaxy is out there. It is here. It is in the space between your hand and this screen, in the space between the walls, in every cubic inch of the emptiness around you. It is doing its slow, relentless work everywhere at once, in the room and in the void between galaxies alike. The only reason you cannot feel it is that on the scale of a room, its effect is unimaginably gentle. Give it the whole universe to work on, and it moves galaxies. There is a further twist hidden inside that gentleness, and it tells you something about the character of the thing. Dark energy is, in absolute terms, extraordinarily faint. If you could bottle up a single cubic meter of empty space and measure the dark energy inside it, you would find an amount of energy equivalent to only a few atoms of hydrogen, one of the lightest things there is. That is almost nothing, a whisper of energy in a volume large enough to hold a person. And yet this whisper, spread across the truly enormous emptiness between galaxies, where there are no atoms and no light and nothing at all to oppose it, adds up to more than 2/3 of the cosmos. The universe is mostly empty, and the emptiness, it turns out, is where the power lives. Ordinary matter clumps into stars and planets and leaves the space between them almost bare. Dark energy does the opposite. It ignores the bright clumped stuff entirely and belongs instead to the vacuum, to the wide dark gaps, which is exactly why it can dominate a universe that looks, to our eyes, as though it is made of stars. It was not always in charge. For the first several billion years after the universe began, ordinary matter and dark matter were dense enough that their gravity ruled, pulling everything together and slowing the expansion down, just as everyone expected. But matter thins out as space expands, growing weaker with every passing eon, while dark energy does not thin out at all. And so, somewhere around 5 or 6 billion years ago, roughly when the Sun and the Earth were forming, the two traded places. The pull of matter faded, the push of the vacuum took over, and the expansion of the universe stopped slowing down and began, quietly, to accelerate. We happen to be living in the era when dark energy won. The physicist who gave the effect its name, Michael Turner, chose those words in 1998 to deliberately rhyme with the older puzzle of dark matter. And the rhyme is honest, because in both cases, the word dark means the same thing. It means we can measure its gravity, and we cannot see it, and we do not know what it is. So we begin not with a distant object, but with a presence, a quiet and enormous presence that surrounds you and that no one on earth understands. Over the course of tonight, I want to walk you slowly into just how strange this presence is. I want to show you how we found it, almost by accident, when the entire community of physicists expected the opposite result. I want to show you why our finest theory, the crown jewel of modern physics, predicts a value for this energy that is wrong by a margin so enormous it barely fits into words. And I want to show you why, of all the unsolved problems in physics, of all the mysteries we could sit with in the dark, this is the one that most deserves to be called disturbing. For now, hold on to the simplest version of the idea, the one you can carry into the rest of the night. Most of the universe is not made of anything we can name. The biggest part of reality is a mystery, and it is not a distant mystery. It is the ground you stand on, and the space you move through, and it is quietly getting larger, even as you lie there. To understand how we discovered that, we have to go back to a night in the late 1990s, when two rival teams of astronomers set out to measure how fast the universe was slowing down, and found, to their shared disbelief, that it was doing nothing of the kind. To understand how we stumbled into the largest mystery in physics, you have to understand what everyone was so sure they would find. In the middle of the 1990s, the great open question in cosmology was not whether the universe was expanding. That had been settled for 70 years, ever since Edwin Hubble and Georges Lemaitre showed that distant galaxies are all rushing away from us, and the farther away they are, the faster they go. The universe was clearly growing. The question was how the growth would end. There were, broadly, two possibilities, and both of them assumed the same thing. Both assumed that the expansion was slowing down. This seemed almost too obvious to question. The universe is full of matter, and matter has gravity, and gravity pulls things together. Every galaxy tugs on every other galaxy, and all that mutual pulling should act as a brake on the expansion, gradually slowing it the way a ball thrown upward is slowed by the Earth. The only real question was whether there was enough matter to eventually halt the expansion and reverse it, pulling everything back into a fiery collapse, or whether the universe would expand forever but ever more slowly, coasting toward a cold and quiet stillness. Fast break or slow break, those were the choices. Nobody serious imagined there was no break at all. So two teams of astronomers set out, in a quiet rivalry, to measure the rate of that slowing. If you could measure how much the expansion had decelerated over cosmic history, you could weigh the universe and read its future. The trick was to find objects far enough away that their light had been traveling for billions of years, carrying information about how fast space was expanding back then, and to compare that with how fast it expands now. But to do that, you needed a way to measure enormous distances precisely, and that is one of the hardest problems in all of astronomy. The solution was a particular kind of exploding star, called a Type Ia supernova. These are among the most useful objects in the sky, and the reason is a small miracle of physics. A Type Ia supernova happens when a dead star, a dense ember called a white dwarf, pulls in matter from a companion until it reaches a critical mass, a threshold of about 1.4 times the mass of our Sun. At that exact tipping point, it detonates in a runaway nuclear explosion. Because every one of these explosions is triggered at nearly the same mass, by the same physics, they all blaze with very nearly the same true brightness. For a few weeks, A single such star can shine as brightly as an entire galaxy of billions of stars, bright enough to be seen across much of the observable universe. And because you know how bright they truly are, you can judge how far away they are by how faint they appear, the same way you could estimate the distance to a candle in the dark if you knew exactly how strong its flame was. Astronomers call such objects standard candles, and Type Ia supernovae are the best standard candles we have for cosmic distances. There is a subtlety worth pausing on, because it is a small triumph of ingenuity. Type Ia supernovae are not perfectly identical. Some are a little brighter, some a little fainter. If that were the end of the story, they would be useless as distance markers, because you could never be sure whether a faint one was truly far away or simply an unusually dim explosion. But in the early 1990s, an astronomer named Mark Phillips noticed a reliable pattern. The brighter supernovae fade more slowly, and the fainter ones fade more quickly, and the relationship between brightness and fading time is precise enough to correct for. By watching how fast a supernova dims over the days after its peak, you can work backward to its true brightness and turn a rough standard candle into an exquisitely calibrated one. This single insight, the Phillips relation, is what made the whole measurement possible. Without it, the acceleration would have stayed hidden inside the scatter. It is also worth remembering how recent the very idea of an expanding universe was. Just a few decades earlier, the astronomer Vesto Slipher had been the first to notice, around 1912, that the light from distant galaxies was shifted toward the red end of the spectrum, stretched as though the galaxies were racing away. Hubble and Lemaitre turned those redshifts into the law of cosmic expansion in the 1920s. So when the two supernova teams set out in the 1990s, the expansion itself was old news, textbook material. Acceleration was something else entirely. It was not a refinement of an old idea. It was a new and unwelcome fact that no one had ordered. One team was the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory in California. The other was the High Z Supernova Search Team, led by Brian Schmidt, with much of the crucial analysis carried out by a young astronomer named Adam Rees. Both teams spent years hunting for these fleeting explosions in distant galaxies, racing telescopes against the few-week window before each supernova faded, gathering the light of stars that had died billions of years before the Earth existed. Both teams were measuring the same thing, and both expected the same answer. They expected to see the fingerprint of deceleration. They expected the distant supernovae to be a little closer, a little brighter, than they would be in a universe that expanded at a steady rate, because a decelerating universe would have been expanding faster in the past, and so would have carried those stars less far. Between the two teams, the whole edifice rested on a surprisingly small number of stars. Only about 50 distant supernovae, carefully measured, carried the weight of the conclusion. That is worth holding in mind, because it tells you how faint and how precious each of these signals is. Each explosion was a single ancient event, its light gathered photon by photon after a journey of billions of years, and from just a few dozen of them, the future of the cosmos was rewritten. The effect itself was not huge in the raw numbers. The distant supernovae came in roughly 10 to 25% fainter than a decelerating universe would allow, a quarter, at most, too dim. But in a measurement this careful, a quarter is a scream. What they found was the opposite. The distant supernovae were too faint. They were fainter than they should be, even in a universe that expanded at a perfectly constant rate, which meant they were farther away than any amount of deceleration could explain. The only way to account for the dimness was almost unthinkable. The expansion of the universe was not slowing down, it had been speeding up. Something was pushing space apart, overwhelming the gravity of all the matter in the cosmos, and it had been doing so for billions of years. I want you to feel how unwelcome this result was. because it is easy, from the comfort of hindsight, to imagine the discovery as a moment of triumph. It was not, at least not at first. It was closer to a crisis. Both teams assumed they had made a mistake. There were 100 ways to be fooled. Perhaps distant supernovae were intrinsically dimmer than nearby ones. Perhaps clouds of cosmic dust were absorbing their light and making them look farther away than they were. Perhaps some subtle error had crept into the calibration. The teams spent months, working largely in parallel and in competition, hunting for the flaw that would make the strange result go away. They checked the dust. They checked the calibration. They checked whether the ancient supernovae might be built differently from modern ones. One by one, the mundane explanations fell away, and the impossible answer refused to leave. By the time both teams published in 1998 and 1999, they had arrived, independently, at the same conclusion, and the fact that two rival groups, using somewhat different methods, reached the same impossible result is a large part of why the community came to believe it. This is how science guards itself against wishful thinking. When your competitors, who would be delighted to prove you wrong, instead confirm your most uncomfortable finding, you are looking at something real. The universe was accelerating. In 2011, Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics for the discovery. But here is the sentence that matters most, the one to carry into the rest of the night. Winning the highest honor in science for discovering an effect is not remotely the same as explaining it. The three astronomers were not rewarded for understanding what was pushing the universe apart. Nobody understood it then, and nobody understands it now. They were rewarded for proving, beyond reasonable doubt, that the pushing is real. They had found the effect and named it, and the name they and their colleagues settled on was dark energy. What they had not done, what no one has done in the quarter century since, is answer the only question that really matters. They had shown that the largest force shaping the fate of the universe exists. They could not say what it was. There is a human texture to that moment that is easy to lose in the summary. These were not scientists hoping to overturn the established picture. They had built their careers, their instruments, and their expectations around measuring a deceleration, and the data kept handing them a number with the wrong sign. Adam Rees has described going back to the analysis again and again, half hoping to find the bug that would make the embarrassment disappear, and finding instead that the result only grew firmer the harder he pushed on it. There is a particular kind of unease in that. The unease of a careful person watching their own trustworthy method insist on an answer they do not want to believe. That unease is the true birthplace of dark energy. It was not announced with fireworks. It was conceded, reluctantly, by people who had run out of ways to make it go away. That is the strange inheritance of 1998. We came looking for the rate at which the universe was slowing down, fully expecting a modest, sensible answer, and instead, we found a universe accelerating under the influence of something we could measure but could not comprehend. The ground of settled science shifted underfoot, and it has not stopped shifting since. And to understand why the acceleration is so much stranger than it first appears, we need to be very precise about what that word, accelerating, actually means when we apply it not to a car or a falling ball, but to space itself. We use the word expansion so casually that it hides how strange the reality is. When you hear that the universe is expanding, it is natural to picture galaxies flying outward through space, like debris hurled from an explosion, racing away into some pre-existing emptiness. That picture is wrong, and correcting it is the first step toward feeling why dark energy is so unsettling. Galaxies are not flying through space. Space itself is expanding, swelling, growing new distance between things that are not moving at all. The galaxies are, for the most part, sitting still. It is the space between them that is being stretched. This is not a metaphor or a figure of speech. It is the literal content of Einstein's theory of gravity, general relativity, which describes space and time as a flexible fabric that can bend, curve, and stretch. In that theory, the distance between two distant galaxies can grow without either galaxy going anywhere, because the very thing that distance is measured in, space, is being manufactured between them. Imagine two dots drawn on the surface of a balloon. As you inflate the balloon, the dots move apart, but neither dot travels across the rubber. The rubber itself expands, and the dots are carried along. Now forget the balloon's surface, and imagine that stretching happening in all three dimensions at once, everywhere, with no edge and no center. That is the expansion of the universe. There is no point it is expanding from, and no point it is expanding into. Every place sees every distant place receding, as though it were the center, because there is no center at all. The balloon picture captures one more thing that is easy to miss, and it is the key to everything that follows. On an inflating balloon, two dots that start close together drift apart slowly, while two dots on opposite sides of the balloon rush apart quickly. The farther apart two dots are, the more rubber lies between them, and the more rubber there is to stretch, so the faster they separate. The universe behaves exactly this way. A galaxy twice as far from us recedes twice as fast. A galaxy 10 times as far recedes 10 times as fast, because there is simply more expanding space between us and it. This is the law Hubble and Lemaitre found a century ago, and it means the recession speeds are not the same everywhere. They grow with distance, without limit. Swap the balloon for a loaf of raisin bread rising in an oven, and the picture holds. As the dough expands, every raisin moves away from every other raisin, and the distant raisins move away fastest, and no raisin is at the center, because there is no center. Each raisin, if it could look around, would swear it was the still point, and everything else was fleeing from it. For most of cosmic history, that stretching was slowing down, restrained by the gravity of all the matter riding along inside it. What the supernovae revealed is that the stretching is now speeding up, and this is where the strangeness deepens, because acceleration of the expansion means something very specific and very odd. It means that the rate at which new space appears is itself increasing. Every second, space grows. And because there is more space this second than there was last second, next second it will grow even faster. The expansion feeds on itself. The more space there is, the more space it makes. And the more space it makes, the more there is to make still more. Follow that logic to its conclusion, and you arrive at something genuinely difficult to hold in the mind. A distant galaxy, carried along on the swelling of space, recedes from us faster the farther away it is. Far enough away, and the space between us and it grows so quickly that the galaxy is effectively receding faster than light, not because it is moving through space faster than light, which nothing can do, but because so much new space is appearing between us that no signal could ever cross the widening gap. Such galaxies have, in a real sense, already left our universe. Their light will never reach us again. And as the expansion accelerates, more and more of the cosmos is quietly slipping across that threshold, out of contact, forever. There is a boundary that marks this point of no return, and physicists call it the cosmic event horizon. It sits at a distance of roughly 16 billion light-years, and it is not a wall or an edge so much as a line beyond which the expanding space wins the race against light. A photon emitted just outside that horizon, aimed straight at us, will swim toward us for the rest of time and never arrive, because the space it must cross grows faster than it can advance. It is the same kind of horizon as the edge of a black hole, only turned inside out. A black hole has a boundary you cannot escape from within. The accelerating universe has a boundary you cannot reach from outside. In both cases, the horizon is drawn not by any material barrier, but by the behavior of space and light. And in both cases, things cross it and are lost to us. The difference is that the black hole's horizon is a fixed feature of a single object, while the cosmic horizon belongs to us, and everything in the universe is slowly drifting toward it. I want to slow down here and bring this close, because it is tempting to keep dark energy at a safe astronomical distance, and the truth is that it is not distant at all. Sit still for a moment, perfectly still. Feel the weight of your body, the quiet of the room, the fixed and solid geometry of the walls around you. Now understand that the stillness is an illusion of scale. In the space between your hand and the wall, new space is appearing. In the gap between the earth and the sun, new space is appearing. It is happening right now, everywhere in the room, everywhere in your body, in every cubic inch of the dark. You feel none of it, and for a simple reason. Inside the room, inside your body, inside the solar system, the bonds that hold things together, the electrical forces between atoms, the gravity binding the planets to the sun, are overwhelmingly stronger than the feeble outward push of the expanding vacuum. The space tries to grow, and the bonds quietly hold it in place, winning the contest so completely that you never noticed there was a contest at all. Your body is not getting larger. The earth is not drifting from the sun. The atoms in the wall are held fast. But out there, in the enormous gaps between galaxies, where there are no bonds strong enough to resist, the space wins. It stretches unopposed, carrying whole galaxies apart, and it does so a little faster every moment. The same gentle pressure that cannot budge the atoms in your hand is, on the grand scale, the most powerful influence in the universe. Try to picture the numbers, not to memorize them, but to feel the imbalance. The rate at which space expands amounts to roughly 70 kilometers per second for every 3.3 million light-years of distance. Across the width of a room, that rate is so close to zero that the whole age of the universe would not stretch the room by the width of a single atom. Across the gap between the Earth and the Sun, it is still hopelessly outmatched by the Sun's gravity. But lay that same gentle rate across the millions of light-years between galaxies, and it becomes a separation of hundreds of kilometers every second, growing without end. The push per inch of space is almost unimaginably weak. There is just so much space. The universe wins not by strength, but by sheer extent, the way a whisper repeated across a billion voices becomes a roar. That is the vertigo I want you to feel, not fear, just the quiet dislocation of realizing that the ground of reality, the space you have always thought of as simple nothingness, as the empty stage on which events happen, is not a stage at all. It is a participant. It has a life of its own. It grows. Once you accept that space itself is doing something, that the emptiness is active rather than inert, a new and obvious question forces itself forward, and it is the question that will occupy us for the rest of the night. If space is expanding faster and faster, something has to be driving it. Acceleration does not happen for free. When a car speeds up, fuel is burning. When a ball speeds up, a force is pulling it. So what is the fuel of the cosmos? What force reaches into every cubic inch of empty space and pushes it to grow? There is something deeply counterintuitive buried in that requirement, and it is worth naming before we go on. In everything you have ever experienced, gravity pulls. Masses attract. Drop a coin and it falls. Throw it up and gravity drags it back. For the expansion of the universe to speed up, gravity would have to push, to repel, to drive things apart, rather than draw them together. That sounds impossible, and in the world of ordinary matter, it is. But Einstein's equations contain a loophole almost nobody expected to matter. In general relativity, it is not only mass that gravitates, pressure gravitates too, and a substance with the right kind of pressure, a strange negative pressure, a tension woven through space, produces not attraction, but repulsion. So the search for the fuel of the cosmos is really a search for something with this bizarre property, an energy filling the vacuum, whose pressure is negative, whose very presence bends space so as to push it apart. For the expansion to accelerate, the emptiness must contain energy, a kind of energy that does not thin out as space grows, an energy woven into the vacuum itself. And the moment you say that empty space contains energy, you have wandered, perhaps without realizing it, into one of the oldest and strangest ideas in modern physics, an idea that Albert Einstein himself introduced, then discarded in embarrassment, and that came roaring back nearly a century later to become our best explanation for the largest mystery in the cosmos. To understand dark energy, we have to understand the energy of nothing. The story of dark energy has a strange prologue, written more than 80 years before anyone measured an accelerating universe. It begins with Albert Einstein, in 1917, staring at his own equations and not liking what they told him. Einstein had just completed general relativity, his masterpiece, the theory that recast gravity as the bending of space and time. When he applied it to the universe as a whole, the equations delivered an unwelcome verdict. They said the universe could not sit still. A cosmos full of matter, all of it gravitationally attracting all the rest, would inevitably either collapse inward under its own weight or fly apart. It could not simply be static and eternal, which is exactly what Einstein and nearly everyone else at the time believed it was. The idea of an expanding universe had not yet arrived. The galaxies had not yet been shown to be racing away. So Einstein did what a careful theorist does when a beautiful theory disagrees with what seems obviously true. He adjusted it. He added a single new term to his equations, represented by the Greek letter lambda, and called it the cosmological constant. Its job was to hold the universe still. Lambda acted as a kind of built-in outward tendency of space, a gentle repulsion woven into the vacuum, precisely tuned to balance the inward pull of all the matter and keep the cosmos in perfect, delicate equilibrium. It was a fudge, and Einstein knew it was a fudge, but it saved the appearance of a static universe, and for a little while it did its job. It is worth appreciating how fragile Einstein's fix really was, because the fragility foreshadows everything that came later. The balance lambda provided was not stable. It was like a pencil standing perfectly on its point. In principle, it can be done, if the outward push and the inward pull are matched with infinite precision. In practice, the slightest nudge sends it toppling, one way or the other, into collapse or into runaway expansion. A Russian physicist named Alexander Friedmann worked out the full family of solutions to Einstein's equations in the early 1920s and showed that the natural state of a universe, governed by general relativity, is to be dynamic, to expand or contract, not to sit still. A Belgian priest and physicist named Georges Lemaitre reached a similar conclusion and went further, proposing that the universe had begun from a single primeval point and had been expanding ever since. The mathematics was telling everyone who would listen that the cosmos moves. Einstein had heard it too. He had simply refused to believe his own equations over his intuition that the heavens were eternal and unchanging. Then the ground moved. In the 1920s, Edwin Hubble showed that the universe was not static at all. The galaxies were flying apart. The universe was expanding, exactly as the undoctored equations had tried to say all along. The whole reason for lambda evaporated. Einstein had bent his own theory to prevent it from predicting an expanding universe, and then the universe turned out to be expanding. He removed the term, and according to a story told by the physicist George Gamow, Einstein called the cosmological constant the biggest blunder of his life. It became a cautionary tale, the great man's one famous stumble, a piece of mathematical cowardice he should never have committed. For most of the 20th century, lambda was a footnote, a discarded idea, something you mentioned only to warn students against fudging their equations. And then, in 1998, the discarded idea came back from the dead. When the two supernova teams found that the expansion was accelerating, physicists reached into the drawer, where they had filed Einstein's abandoned term and pulled it out again. Because it turns out that lambda, the cosmological constant, is precisely the thing you need to make a universe accelerate. Einstein had introduced it to hold the cosmos still, set it a little stronger than the balance point, let its outward push exceed the inward pull of matter, and instead of holding still, the universe speeds apart, faster and faster, exactly as the supernovae showed. Einstein's blunder was not a blunder. It was a premonition. He had written down the mathematics of dark energy decades before there was any evidence it existed, and then talked himself out of believing it. There is a lesson buried in that reversal, and it is a humbling one. The equations were wiser than the man who wrote them. Einstein trusted his gut over his mathematics, and his gut was wrong. It is the kind of story that should make anyone cautious about deciding, in advance, what the universe is allowed to do. The cosmos has never felt any obligation to match our sense of what is reasonable, and dark energy, as we are about to see, is the place where that indifference becomes almost unbearable. What is lambda, physically? This is where we arrive at the idea I promised you, the idea that empty space is not empty. The cosmological constant behaves as though every cubic inch of the vacuum, every scrap of truly empty space, contains a fixed amount of energy, not energy that is passing through, not radiation or particles that happen to be there, but energy that belongs to the space itself, an intrinsic property of nothingness. Take a region of space and remove everything from it, every atom, every photon, every trace of matter and light, until it is as empty as emptiness can be, and according to this idea, there is still energy there, woven into the fabric, and that energy has the strange negative pressure we spoke of, the tension that pushes space apart. It helps to sit with just how alien this claim is, because our whole intuition rebels against it. From childhood we are taught that a vacuum is the absence of everything, that empty means empty, that nothing is, well, nothing. To say that empty space has energy sounds like saying that silence has a sound, or that darkness has a color. Yet this is exactly what the mathematics of dark energy requires, and, as we will see in a moment, it is also what our theory of the very small independently insists upon. The vacuum, in modern physics, is not an absence. It is a presence with properties. It has an energy, and that energy has a pressure, and that pressure shapes the largest structures in the universe. Empty space is not empty. Hold on to that phrase, because we will return to it, and each time we do it will mean something a little heavier than it did before. There is even a name for a universe made of nothing but this vacuum energy, a universe swept clean of all matter and radiation and left with only lambda. It is called a de Sitter universe, after the Dutch astronomer Willem de Sitter, who found the solution to Einstein's equations back in that same busy decade. A de Sitter universe does not sit still, and it does not collapse. It expands exponentially, doubling in size, then doubling again in the same interval, and again, forever, an eternal accelerating growth, driven purely by the energy of empty space. And here is the sobering part. As dark energy comes to dominate our own cosmos more and more completely, as matter thins toward irrelevance, our universe is slowly turning into a de Sitter universe. We are watching the cosmos converge, over billions of years, on the pure expansion of empty space. Here is the property that makes it able to dominate the universe, and it is worth stating slowly, because it is the crux. When space expands, ordinary matter thins out. Double the volume of a box of gas, and the gas becomes half as dense. The same atoms are spread over twice the space. Energy that belongs to the vacuum does not behave this way. Because it is a property of space itself, every new cubic inch of space that the expansion creates comes with its own full ration of vacuum energy. The density does not fall. Double the volume, and you simply have twice as much vacuum energy, at the same density as before. Matter dilutes, the vacuum does not. And so, as the universe expands and matter grows ever more thinly spread, the vacuum energy holds its ground, unchanging, patient, until inevitably it comes to dominate. This is why dark energy was weak in the early universe and rules the cosmos now. It did not grow stronger. Everything else grew weaker around it, and it was simply left standing. Physicists capture this behavior in a single number, called the equation of state, written with the letter W. It is the ratio of a substance's pressure to its energy density, and it tells you how the substance responds to the expansion of space. For ordinary matter, W is essentially 0. For radiation, it is 1/3. For a true cosmological constant, for energy that belongs to the vacuum and never dilutes, W is exactly -1. That minus sign is the whole story. It is the mathematical signature of the negative pressure, the tension in the vacuum, the thing that pushes rather than pulls. And when astronomers measure the properties of dark energy across billions of years of cosmic history, the value of W they find sits astonishingly close to -1, right on the number that a pure cosmological constant, a pure energy of empty space, would produce. So the simplest and best-fitting explanation for dark energy is Einstein's resurrected fudge factor, the energy of the vacuum, a constant density of tension filling all of space and never fading. It fits the supernovae. It fits the arrangement of galaxies. It fits the afterglow of the Big Bang. By every measurement we can make, the vacuum appears to have energy, and that energy appears to be driving the cosmos apart. It is a beautiful, economical answer. There is only one problem with it, and it is not a small one. When we try to calculate, from our deepest theory of how the universe works, exactly how much energy empty space should contain, we get an answer. And the answer is catastrophically, historically, almost comically wrong. We now have two pictures of empty space, and they come from the two greatest achievements of modern physics. From general relativity, from the study of the very large, we learn that the vacuum has an energy, small and steady, gently pushing the universe apart. From quantum theory, from the study of the very small, we learn what that vacuum energy ought to be. And when you put the two together, you get the single most embarrassing result in the history of science. To see why, we have to look closely at what empty space is, according to quantum mechanics, because it is nothing like the placid nothingness of common sense. In the quantum picture, the vacuum is not calm, it seethes. Every point in space is filled with fields, invisible entities that stretch through everything, and these fields can never be perfectly still. The uncertainty principle, the fundamental rule at the heart of quantum theory, forbids it. A field that was perfectly quiet, perfectly zero, everywhere and always, would be too precisely defined to be allowed. So instead the fields jitter, forever. With a restless energy they can never shed, particles flicker into existence and vanish again in unimaginably brief instants, borrowing energy from the vacuum and paying it back before the universe can notice. Physicists call these virtual particles, and they are not a fantasy. Their effects have been measured in the laboratory to extraordinary precision, in tiny shifts of atomic energy levels, and in faint forces between metal plates held a hair's breadth apart. The seething vacuum is real. Empty space is not empty. It is a boiling sea of quantum activity, and all that activity carries energy. It is fair to ask how we can possibly know that the vacuum seethes if it is empty by definition, and the answer is that the seething leaves fingerprints we can measure. In 1948, a physicist named Hendrik Casimir predicted that two uncharged metal plates, held extremely close together in a vacuum, would feel a faint attraction, pushed together by the fact that fewer kinds of quantum jitter fit in the narrow gap between them than in the open space outside. That force has been measured, exactly as predicted. In the same era, careful study of the hydrogen atom revealed a tiny shift in its energy levels, the Lamb shift, that could only be explained by the atom's electron interacting with the restless vacuum around it. Both results say the same thing: the vacuum is not inert. It is full of quantum activity with real, measurable consequences. So, when quantum theory tells us the vacuum has energy, it is not speculating about something invisible. It is describing the same seething emptiness, whose effects we can weigh in a laboratory. The energy is real. It is only the amount that goes so catastrophically wrong. So here is the natural question, the one any physicist would ask. If the vacuum is full of this restless quantum energy, how much energy is it? Add up all the jitter of all the fields, all the flickering of all the virtual particles, and what total do you get for the energy of a cubic inch of empty space? Because whatever that total is, it should be the cosmological constant. It should be the dark energy, the vacuum energy that quantum theory predicts, and the vacuum energy that drives the universe apart, should be one and the same thing. This is not a wild hope. It is the most natural identification in the world. The vacuum has energy according to relativity, and quantum theory tells us the energy of the vacuum. They should match. They do not match. They miss each other by a margin so enormous that when you first encounter it, you assume you have misread the number of zeros. When physicists carry out the calculation, summing the quantum jitter of the fields up to the highest energies where our theories still apply, up to the Planck scale where gravity itself becomes quantum, they arrive at a predicted vacuum energy that is larger than the observed dark energy by a factor of about 10 to the power of 120. That is a 1 followed by 120 zeros. The prediction is not a little too big. It is not off by a factor of 10, which would be a bad day, or a factor of 1,000, which would signal something seriously wrong. It is too big by a factor of 1, followed by 120 zeros. I want to make this number real, because it is so large that it slips through the mind without leaving a mark, and the whole force of the mystery depends on feeling its size. Consider the number of atoms in the entire observable universe. Every atom in every star, in every galaxy we could ever see. That number is about 10 to the power of 80, a 1 followed by 80 zeros. It is already beyond any human intuition. Now understand that the error in the vacuum energy prediction is not 80 zeros. It is 120. The discrepancy is larger than the number of atoms in the universe, and then larger than that again by a factor of 10 to the 40th. There is no honest analogy that reaches it, but people have tried. One way to put it is this. Imagine you calculated, from careful and trusted principles, that an object should weigh 5 pounds. You pick it up, and it weighs 5 pounds, followed by 120 zeros of pounds, a weight so far beyond the mass of the entire universe that the comparison loses all meaning. That is the scale of the disagreement between our theory of the vacuum and the vacuum we actually live in. Someone might object that the Planck scale is an extreme place to cut off the calculation, and that is fair. So consider the mildest, most conservative version of the estimate. Even if you stop the sum far lower, at the energy scale where the everyday particles of the Standard Model live, well within territory our accelerators have thoroughly explored, the predicted vacuum energy still overshoots the observed value by something like 55 orders of magnitude. 55 zeros, not 120, but still a disagreement so enormous it dwarfs every other error in the history of measurement. There is no reasonable place to draw the line that rescues the prediction. Cut it off high, and you are wrong by 120 orders of magnitude. Cut it off low, and you are wrong by 55. Every honest choice lands you far inside the impossible. There is one more way to state the smallness, and it may be the most haunting. If you measure the observed dark energy in the natural units of fundamental physics, the units built from the speed of light, the quantum of action, and the strength of gravity, the so-called Planck units, in which most fundamental quantities come out close to 1, the cosmological constant comes out as a number around 10 to the minus 122. It is, as far as anyone knows, the smallest non-zero number that appears anywhere in all of fundamental physics. Nature seems to have taken a dial that our theories say should read 1, or something near it, and turned it down to 122 decimal places of zeros, before finally, in the very last digits, allowing it to be something other than nothing. And on that last, almost invisible digit hangs the existence of everything. Physicists have names for this. They call it the cosmological constant problem, and in candid moments they use blunter language. It has been called the worst theoretical prediction in the history of physics. It has been called the largest discrepancy between theory and experiment in all of science. These are not the words of outsiders mocking the field. They are the words of physicists describing their own most successful theories, because that is the part that makes it so hard to bear. Let this settle, because it is the emotional center of the entire subject, the place where the mystery stops being a curiosity and becomes something closer to vertigo. Quantum field theory, the framework that produces this absurd prediction, is not a shaky or speculative idea. It is the most precisely tested theory humanity has ever built. It predicts the magnetic behavior of the electron and matches the measurement to 12 decimal places, an agreement so exact it is like predicting the distance from New York to Los Angeles and being correct to within the width of a human hair. Nothing in the history of science has ever been confirmed so thoroughly, and this same theory, our crowning triumph, the finest instrument of prediction the human mind has ever produced, when turned on the largest single ingredient of the universe, is wrong by a factor of 1, followed by 120 zeros. It is simultaneously the most accurate and the most catastrophically mistaken thing we have ever built. Sit with the strangeness of that. We are not in the ordinary situation of a theory that works until it reaches its limits and then gently breaks down. We are in a far stranger situation. The same theory is, on one question, correct to a part in a trillion, and on another question, wrong by more than the number of particles in existence. It is as if a master watchmaker built a timepiece that kept perfect time for 1,000 years and was also, somehow, off by 1 billion years. Both things are true of the same watch. Both things are true of the same physics, and nobody knows how to reconcile them. You might reach for the obvious escape. Perhaps the different contributions to the vacuum energy cancel out. Perhaps the positive jitter of some fields is precisely balanced by the negative jitter of others, so that the enormous predicted energy mostly annihilates itself, leaving only the tiny amount we observe. This is a reasonable hope, and physicists have explored it seriously. A symmetry of nature called supersymmetry, if it were exact, would produce exactly this kind of cancellation, matching every field against a partner of opposite sign, so that their vacuum energies wipe each other out. But supersymmetry, if it exists at all, is not exact in our universe. It is broken, and the particles it would predict have not shown up in our most powerful accelerators. A broken symmetry gives an imperfect cancellation, and an imperfect cancellation still leaves a residual vacuum energy enormously larger than what we see, dozens of orders of magnitude too big, even in the most optimistic accounting. The cancellation idea does not rescue us. It only changes the size of the catastrophe from unthinkable to merely impossible. So we are left staring at the central scandal of modern physics. Our best theory of the small predicts that empty space should contain an almost infinite density of energy, enough to have ripped the universe apart in its first instant, enough that no galaxy, no star, no planet, no living thing could ever have formed. And instead, the vacuum contains a whisper, a faint tension, 120 orders of magnitude gentler, precisely weak enough to let a universe exist and grow and, eventually, wonder about itself. Why is the vacuum energy so small? Not zero, which we might at least explain with some perfect cancellation, but small, tiny, and stubbornly non-zero. That question has no accepted answer. It is, possibly, the deepest unsolved problem in all of physics, and it lives in the empty space of the room you are lying in right now. Every physicist who has looked hard at this problem has felt the same quiet unease, the sense of standing at the edge of something that should not be possible, a gap in understanding so wide that it cannot be a mere detail waiting to be tidied up. A discrepancy of this size is not a loose thread. It is a sign that something fundamental about how we understand energy, or space, or gravity, or all three, is simply missing, and no one yet knows what. The cosmological constant problem has a second face, and it is somehow even more unsettling than the first. It is not only that the vacuum energy is far smaller than our theory predicts, it is that the exact value it happens to have sits inside an almost impossibly narrow window, a window so precisely placed that if the number were even slightly different, you would not be here to wonder about it. Let me explain what I mean, because this is the point where dark energy stops being an abstract accounting error and becomes a statement about your own existence. Dark energy pushes space apart. Gravity pulls matter together. Everything you love about the universe, every galaxy, every star, every planet, every possibility of life, depends on gravity having won the early rounds of that contest, on matter being able to clump together into structures before the expansion swept it all too thin. In the young universe, matter was dense and dark energy was faint, so gravity won, and galaxies formed. But this only worked because dark energy was weak enough to stay out of the way during those crucial early eons. Now imagine turning up the dial. Suppose the vacuum energy had been larger, not by the full 120 orders of magnitude that our theory predicts, but by a far more modest amount, just a few dozen times stronger, or a few hundred. Even that gentle increase would have been fatal. A universe with more dark energy would have begun accelerating much earlier, while matter was still trying to gather itself. The expansion would have pulled the young cosmos apart before gravity could assemble a single galaxy. No galaxies means no stars. No stars means no planets, no carbon, no oxygen, no chemistry, no life. A universe with substantially more dark energy is a universe of thin, cold gas, expanding into darkness, containing nothing that could ever look up and ask why. It would not be a hostile universe so much as an empty one, a smooth grey nothing, stretching itself thinner forever, with no islands of matter, no furnaces to forge the heavier elements, no worlds and no witnesses. The difference between that sterile cosmos and the one we actually inhabit, brimming with galaxies and chemistry and life, comes down to the value of a single faint energy in the vacuum, and to the fact that ours happens to be almost unaccountably small. And the terrible thing is, how little of an increase it would take. The value we observe is not comfortably in the safe zone. It is close to the edge, in the narrow band where structure is just barely possible. There is a remarkable footnote to this, and it is one of the few times in this whole story where physics scored a genuine prediction. In 1987, more than a decade before anyone measured the acceleration, the physicist Steven Weinberg reasoned along exactly these lines. He asked what values of the vacuum energy would still permit galaxies to form, and he found an upper limit, a ceiling above which the universe would be sterile. Then he made a bold argument. If, for whatever reason, the vacuum energy could take many possible values, then observers like us would necessarily find ourselves in a universe where it fell below that ceiling, simply because no observers could exist anywhere else. And so, he suggested, we should expect to measure a value that is small but not quite zero, sitting just under the threshold that allows structure. When the acceleration was discovered in 1998, the value turned out to be roughly in the range Weinberg had anticipated. It was a strange kind of triumph, because it did not explain the vacuum energy so much as explain why we, of all possible observers, would find it small. We will return to what that argument really means, and to how uncomfortable many physicists are with it, but for now hold on to the simple fact. The smallness of dark energy was, in a loose sense, predicted, and the prediction rested entirely on the requirement that a universe be able to contain someone to notice it. This is what physicists mean when they say the cosmological constant appears fine-tuned. The number that governs the fate of the universe sits balanced on a knife's edge, and the blade is razor-thin. Turn the value up, even modestly, and the cosmos is sterile. The fact that dark energy is not merely small, but small in precisely the way required to permit galaxies, stars, planets, and observers, is either the most fortunate coincidence imaginable, or a clue to something we do not yet understand. Either way, it deepens the mystery rather than resolving it. We began by asking why the vacuum energy is so much smaller than predicted. Now we must also ask why it is small in exactly the way that allows us to exist. I want to take you somewhere for a moment, into the thing itself, because the vacuum is where all of this lives, and it is easier to feel than to explain. Shrink down with me, in imagination, into a cube of the emptiest space you can conceive. Not the thin gas between stars, which is crowded by comparison, but the true void, a pocket of space swept clean of every atom, every particle of light, every trace of matter. By the standards of common sense, there is nothing here. It is perfectly dark, perfectly silent, perfectly empty. And yet, as you settle into it, you begin to sense that the emptiness is not still. All around you, too fast and too faint to catch directly, particles are flickering into being and vanishing again, pairs of them appearing out of nothing and annihilating back into nothing before any clock could record them. The void trembles with this activity, a restless hum woven into the fabric of space, never resting, never silent, present in every cubic inch of what you had always been told was nothing at all. And here is the part to hold as you drift in that trembling dark. According to our finest theory, all this seething carries an energy so immense that, by rights, it should have crushed the cosmos in its cradle or torn it instantly to shreds. Instead, the void holds itself in an almost perfect and utterly unexplained restraint, letting slip only the faintest breath of a push, just enough to move galaxies over billions of years, and not one part more. You are floating in the most powerful and most gentle thing in the universe at once, and no one on Earth can tell you why it chose to be gentle. Stay a moment longer in that void, because there is one more thing to notice about it. The energy trembling around you does not care that the space is empty. That is the whole point. Fill the cube with atoms and the vacuum energy is still there, underneath, a property of the space rather than of anything in it. Sweep the atoms away and the energy remains, undiminished. This is why it cannot be diluted, why it does not fade as the universe grows, why it will still be here, at exactly this density, long after the last star has died and the last atom has drifted beyond reach. Matter is a guest in space. Vacuum energy is the house itself. And the house, it turns out, is doing something. It is pushing outward, quietly, patiently, in every direction at once, and it will keep pushing when there is nothing left for it to push against but more of itself. Come back now, to the room, to the weight of your body, to the quiet, but carry the image with you, because it changes the meaning of the ordinary emptiness around you. The space between your hand and the wall is not a passive gap, it is that same trembling void, carrying that same unexplained energy, balanced on that same knife's edge that permits your existence. You are not separate from the mystery, observing it from a safe distance. You are steeped in it. It is the medium you live inside. The vacuum energy is not the only quantity in physics that seems suspiciously well adjusted. and it helps to see it in company. The strength of gravity, the mass of certain fundamental particles, the balance between the forces that bind atomic nuclei, all of these appear to sit within ranges that permit a universe of structure and chemistry, and shift too far in either direction, and you get a cosmos of no stars or no atoms. Physicists argue endlessly about how seriously to take these apparent tunings, and reasonable people disagree. But the cosmological constant is the most extreme case by a wide margin. The others are tunings of a few percent, or a few parts in 1,000. This one is a tuning of 120 decimal places. If the universe is a machine, dark energy is the one setting adjusted with a precision that beggars every other dial on the panel, and adjusted, as far as we can tell, to the exact value that lets the machine produce minds capable of reading its settings. Whether that is destiny, accident, or a signpost toward physics, we have not yet discovered. No one can say. But it is not the kind of thing a careful scientist is willing to wave away. There is a temptation, when facing a fine-tuning like this, to explain it away with a shrug and a word like coincidence. But the word does no work. A coincidence of 1 part in 100 is a curiosity. A coincidence that requires a number to land in a window narrower than 1 part in many, many powers of 10, on pain of a lifeless universe, is not the kind of thing scientists are willing to accept without an explanation. It demands a reason, and the search for that reason has driven physicists towards some of the strangest ideas in the whole of science, ideas we will come to soon, ideas involving hidden fields, or a subtle failure of gravity, or an endless multitude of universes, each with a different vacuum energy, of which we necessarily inhabit one of the rare life-permitting ones. None of these ideas is confirmed. All of them are attempts to answer the same question. Why is the knife balanced so perfectly, when everything we know says it should have fallen? And notice how the two faces of the problem feed each other. The first face asks why the vacuum energy is so much smaller than predicted. The second asks why it is small in exactly the way that permits us to exist. An answer to one is not automatically an answer to the other. A theory could explain why the vacuum energy nearly cancels, yet say nothing about why the tiny leftover lands in the life-permitting window. To solve the mystery fully, you would have to explain both the smallness and the aim, and no one has managed even one, let alone both together. Before we chase those answers, though, it is worth pausing to gather what we have found, because we have accumulated a set of facts that do not sit easily together, and the discomfort of holding them all at once is the true shape of this mystery. Let us step back, for just a moment, and put the pieces on the table where we can see them. We are about halfway through our night together, and this is a good place to stop and gather what we have found, because the pieces we have collected are strange enough that it is worth seeing them all at once. When they sit side by side, the shape of the mystery becomes clearer, and so does the reason it deserves the word disturbing. Here is the first piece. Dark energy is real, and it is the majority of the universe. This is not a fringe idea or a speculative proposal. 3 completely independent lines of evidence: dying stars, the afterglow of the Big Bang, and the arrangement of galaxies across the sky, all point to the same conclusion. Something makes up roughly 68% of everything, and that something is pushing the cosmos apart at an accelerating rate. We can measure how much of it there is too, within a fraction of a percent. On the question of how much dark energy exists and what it does, physics is on solid ground. The measurements are among the most precise in all of science. Here is the second piece. We have a natural candidate for what dark energy is. It is the energy of empty space, the cosmological constant, Einstein's resurrected term, a tension woven into the vacuum, with a pressure so strange it pushes rather than pulls. This candidate fits the data beautifully. Its equation of state, the number that describes its behavior, sits right on the value a true vacuum energy would have. If you wanted to bet on a single explanation for dark energy, This is where the smart money goes. And here is the third piece, the one that turns a tidy story into a crisis. When we take that candidate seriously and calculate, from our deepest and most successful theory of the small, exactly how much energy the vacuum should contain, we get a number that is wrong by a factor of 1, followed by up to 120 zeros. The very theory that gives us the candidate also predicts, for that candidate, a value so enormously off from reality that it stands as the worst quantitative prediction in the history of science. Our best explanation and our worst failure are the same idea, viewed from two directions. Now set those three pieces down together and look at them. We can measure dark energy precisely. We have a compelling explanation for it. And that same explanation, pushed through our finest physics, produces the largest error ever recorded between theory and observation. Each piece is solid on its own. It is only when you hold all three at once that the ground gives way, because they describe a situation that should not be able to exist. We understand this thing well enough to weigh it to 2 decimal places and badly enough to be wrong about it by more than the number of atoms in the universe. Both of those statements are true. Both are established. And no one can yet say how they fit together. It is worth adding a fourth piece to the pile, because it sharpens the first 3. Not only is dark energy real, precisely measured, and catastrophically mispredicted, it is also almost featureless. It does not clump. It does not glow. It has no visible structure, no parts, no behavior we can probe directly the way we probe a particle in an accelerator. Everything we know about it, we know only through its gravity, through the way it bends the expansion of space. We cannot put it in a bottle. We cannot shine a light through it. We cannot run an experiment on a sample of it on a laboratory bench, because it only reveals itself across billions of light years and billions of years. Our entire knowledge of the largest ingredient of the universe comes from watching, at unimaginable distances, what it does to everything else. That is a peculiar kind of intimacy with a stranger. We know its weight and its effect on the fate of all things, and we have never seen its face. This is the honest state of the field, and I want to be clear that the discomfort is not a sign that anyone has made a mistake. The measurements are not in doubt. The precision is not an illusion. The quantum theory that fails so spectacularly here is the same theory that succeeds more precisely than any other human idea. Everywhere else we test it. Nothing is broken in the ordinary sense of a wrong calculation waiting to be corrected. What we have instead is a genuine hole in our understanding, a place where two magnificent theories, general relativity and quantum mechanics, each flawless in its own domain, meet and produce nonsense. Dark energy is where they collide, and the size of the wreckage tells us that something we consider fundamental, some assumption so basic we have not even thought to question it, must be wrong. Think of it as a fault line running through the foundations of physics. On one side stands general relativity, Einstein's theory of gravity and space and time, which governs the large, the cosmic, the slow curving of the universe. On the other side stands quantum theory, which governs the small, the fast, the flickering of particles and fields. For a century, these two theories have both worked flawlessly, each in its own territory, and for the most part their territories do not overlap, so the fact that they have never been fully reconciled has been possible to live with. Dark energy is one of the rare places where the two must speak to each other directly. The energy of the vacuum is a quantum question. Its effect on the expansion of the universe is a gravitational one. And when we force the two theories to a common table and ask them to agree on a single number, they disagree by more than any two theories have ever disagreed about anything. The mystery of dark energy is, at bottom, the sound of our two greatest ideas failing to fit together. That is the true reason this problem haunts physics. It is not a small anomaly, at the edge of knowledge, that a clever graduate student might tidy up next year. It is a contradiction sitting at the very center, involving the largest ingredient of the universe and the two greatest theories we possess. And it will not resolve without a change to something we currently believe with confidence. When a discrepancy is this large and this central, it is not telling you that you got a sum wrong. It is telling you that a whole way of thinking is incomplete. And there is something almost hopeful in that, if you look at it the right way. The great leaps in physics have often come not from small anomalies, but from enormous, stubborn contradictions that refuse to go away, until someone found the hidden assumption that, once dropped, made everything click. The failure of one such assumption gave us relativity. The failure of another gave us quantum mechanics. Dark energy may be a contradiction of exactly that kind, a door we have not yet learned how to open, standing right in the middle of the house. So we have taken the mystery apart and laid it out, and now we can go deeper, because there are further strange facts we have not yet added to the pile. We have not yet asked why dark energy came to dominate exactly now, in the one cosmic era that happens to contain observers. We have not yet looked at the newest measurements, which hint, faintly and controversially, that the constant we have been discussing might not be constant at all. We have not yet followed the mystery to its most personal conclusion, to what dark energy means for the ultimate fate of everything that exists. Each of these makes the picture stranger, not simpler. Let us begin with the timing, with a question so odd that physicists have given it a name of its own. Why now? There is a further oddity about dark energy that is easy to overlook, and once you see it, it is hard to unsee. It concerns timing, and physicists call it the coincidence problem. Recall how differently dark energy and matter behave as the universe expands. Matter thins out. As space grows, the same atoms spread over an ever larger volume, so the density of matter falls, and it falls steeply. Dark energy does not thin out at all. Its density stays fixed, because it is a property of space itself. This means that across the history of the universe, the ratio between the two has changed enormously. In the distant past, when the cosmos was small and dense, matter overwhelmingly dominated. Dark energy was a negligible whisper by comparison. In the far future, when the cosmos has expanded enormously and matter has thinned to almost nothing, dark energy will overwhelmingly dominate by factors of billions and then billions of billions. The balance tips relentlessly from one to the other over cosmic time with no natural stopping point. So here is the strange part. For almost all of cosmic history, one component or the other is thousands or millions or billions of times larger than its rival. There is only a brief window, a thin slice of the universe's whole timeline, during which the two are comparable, during which matter and dark energy contribute roughly similar amounts to the total. And we happen to live in exactly that window. Right now, matter makes up about 30% of the cosmic energy budget, and dark energy about 70%. Those are numbers of the same rough size. A few billion years earlier, matter would have dominated overwhelmingly. A few billion years later, dark energy will. But right now, in our cosmic moment, the two are within shouting distance of each other. Why should we find ourselves alive at precisely the rare epoch when the changing of the guard is taking place? To feel how narrow the window is, think about the sheer span of time on either side of it. The universe is about 13.8 billion years old today, and if dark energy is a true constant, it will keep expanding, forever, with no end. That is an infinite future stretching ahead, during which dark energy will dominate more and more completely. Behind us lie billions of years in which matter ruled. The era of rough balance, the era in which we live, is a mere sliver pressed between an enormous past of matter dominance and an infinite future of dark energy dominance. If you scattered observers randomly across the entire timeline of such a universe, almost none of them would land in the crossover window. It is a coincidence of cosmic proportions that we did, and coincidences of that magnitude, as we have seen, tend to make physicists deeply uneasy. There is a way of framing this that makes it feel even stranger. Imagine the whole future history of the cosmos compressed into a single long day. For that entire day, from before dawn until long past midnight, and on into an endless night, dark energy grows in relative strength, while matter fades. The moment when the two are equal, the moment of handover, is a single brief instant somewhere in that day, and here we are, awake and looking around, precisely at that instant. Either we are extraordinarily lucky, or the timing is not luck at all, but a clue, a sign that dark energy and matter are somehow linked in a way our simplest model does not capture. You can feel how this compounds the fine-tuning we met earlier. It is not only that the vacuum energy has a strangely small value, it is that this value places the crossover, the moment when dark energy overtakes matter, right around the present day, in the same era that produced planets, and chemistry, and observers. If dark energy were a little stronger, the crossover would have come earlier, before galaxies could form. A little weaker, and it would come far in the future, and we would be living in a matter-dominated cosmos still slowing down. Instead, we sit almost exactly at the hinge. Some physicists suspect the coincidence is not as sharp as it first looks, and their reasoning is worth hearing, because it connects the timing to us. Stars like the Sun take billions of years to form, and the heavy elements needed for planets and chemistry have to be forged inside earlier generations of stars and scattered by their deaths before worlds like ours can assemble. All of that machinery runs on a clock of several billion years. And it happens that several billion years is also roughly how long it takes, in a universe with our value of dark energy, for the crossover from matter dominance to dark energy dominance to arrive. So perhaps observers can only appear around the time the handover is happening, not because the universe arranged itself for us, but because the same slow cosmic clock governs both the making of planets and the tipping of the energy balance. It is a partial comfort. It ties the timing of our existence to the timing of the crossover without invoking magic, but it still leans on the peculiar value of dark energy being what it is, and so it pushes the mystery back a step rather than dissolving it. There are answers on offer, though none is fully satisfying. One line of thinking connects the timing to the formation of galaxies and stars, arguing that observers can only arise a certain span of time after the universe becomes hospitable, and that span happens to land near the crossover for reasons rooted in how structure forms. This softens the coincidence, but does not dissolve it. Another line of thinking suspects that the coincidence is a hint that dark energy is not a fixed constant after all, but something dynamic that is somehow linked to the density of matter, so that the two track each other, and their rough equality now is not an accident, but a consequence. That idea is appealing, and it leads directly to the newest and most unsettling development in the whole story, because in the last 2 years, the measurements have begun, very faintly, to suggest that dark energy might indeed be changing. The constant we have spent this whole night discussing may not be constant at all. To see why physicists are suddenly whispering about that possibility, we need to travel to a mountaintop in the Arizona desert, to a machine that has been quietly assembling the largest map of the universe ever made. On a mountaintop called Kitt Peak, in the Sonoran Desert of Arizona, there is a telescope that has been quietly doing something no instrument before it could do. Its name is the Dark Energy Spectroscopic Instrument, DESI for short, and it was built for a single purpose. It measures dark energy by mapping the universe in 3 dimensions, galaxy by galaxy, on a scale never before attempted. Picture the machine at work. It is night. The desert air is cold and dry, and the great dome of the telescope stands open to the sky. Inside, at the focus of a 4-meter mirror, sit 5,000 tiny robotic positioners, each holding an optical fiber no thicker than a hair. Between exposures, in the space of a couple of minutes, all 5,000 of them reposition at once. A soft mechanical rustle in the dark, each fiber swinging to catch the light of one specific, distant galaxy. The dome breathes in starlight. Every fiber drinks the glow of a single galaxy, some of them so far away that their light set out billions of years ago, and feeds it down into instruments that split the light into its colors and read, from the stretch of those colors, exactly how much the universe has expanded since that light began its journey. Night after night, for years, the machine repeats this, 5,000 galaxies at a time, building a map of tens of millions of them, a 3-dimensional chart of where everything sits and how fast the space between it all has been growing. It is the largest map of the cosmos ever made. There is a quiet human drama in a project like this, and it is not the drama of a lone genius at a chalkboard. It is the drama of patience and restraint. Hundreds of scientists across many countries feed this machine and check its output. And when a hint of something extraordinary appears in the data, the culture of the field pushes hard in the opposite direction, toward doubt. Before anyone is allowed to feel excitement, the result must survive every attempt to kill it. Could a flaw in the instrument produce this tilt? Could a bias in how the galaxies were selected? Could the way the data were analyzed have nudged the answer? A team that has spent years building the most precise map of the universe ever made knows better than anyone that a hint is not a discovery, and the caution you hear in their published words is not timidity. It is the discipline that keeps science honest. They are the people most likely to be right, and they are the people least willing to say so. And inside that map lives a ruler. Remember the sound waves that rippled through the hot early universe and froze into a preferred distance between galaxies, a separation of about 490 million light-years. That frozen scale is a standard ruler, laid across the sky, and by measuring how long it appears at different distances, DESI can trace the expansion history of the universe with a precision no earlier survey could match. This is not the flickering light of exploding stars. It is a completely different method, an independent way of reading the same history, and it is exquisitely sensitive to how dark energy has behaved over billions of years. Here is what the machine seems to be finding, and I have to choose my words carefully, because this is the living edge of the science, where nothing is yet settled. When the DESI team took their measurements and asked whether the data preferred a dark energy that stays perfectly constant, a true cosmological constant with an equation of state locked at -1, or a dark energy that changes over time, the data leaned, gently but persistently, toward change. In their 2025 analysis, combining the DESI map with the afterglow of the Big Bang and with catalogues of supernovae, the preference for an evolving dark energy over a constant one reached, depending on which supernova sample was folded in, as high as 4.2 on the scale physicists use to measure statistical significance, with a range beginning around 2.8. For the DESI map combined with the cosmic afterglow alone, the preference sat near 3, with a best fit picture in which dark energy today has an equation of state around -0.42, and a rate of change that suggests it was more negative in the past. Read those numbers plainly, and they describe something remarkable. They hint that in the early universe, dark energy may have been even more powerfully repulsive than a cosmological constant, and that it has since weakened, easing off over billions of years, drifting toward a gentler value today. If that is true, then the thing we have spent this whole night calling a constant is not constant. It is dynamic. It has a history. It rose and it is fading, like something alive, and the simplest and most elegant explanation Einstein's fixed energy of the vacuum, would be wrong in a brand new way. There is a particular detail in the DESI picture that makes theorists especially uneasy, and it is worth understanding, because it shows how a hint can be both exciting and suspicious at once. The best fit story has dark energy crossing from one side of a line to the other. In the past, it behaved as what physicists call phantom energy, with an equation of state below -1, more repulsive than a pure vacuum. Today, it sits above -1, gentler. That crossing, from phantom to non-phantom, is not something the simplest models can do. A single, well-behaved field, rolling slowly through space, tends to stay on one side of that line. Making it cross over requires more elaborate machinery, exotic fields, or unusual couplings that many physicists find contrived. So the very shape of the signal is a double-edged thing. If it is real, it points toward physics stranger than the standard alternatives. If it is an artifact, the fact that it demands such awkward theory is a reason for suspicion. Then there is the matter of the supernovae, and this is where the caution sharpens. DESI's map of galaxies is one ingredient. To get the strongest signals, the team combines it with catalogues of Type Ia supernovae, the same standard candles that discovered acceleration in the first place. But there are several such catalogues, assembled by different groups over different years, and they do not all give the same answer. One catalogue yields only a mild hint of evolution. Another yields a stronger one. The strongest signal of all comes from the newest and largest supernova sample. And precisely because it is new and large, the debate over its possible systematic errors, subtle biases in how the brightnesses were calibrated across the sky and across cosmic time, is most active. When your headline result depends on which of several imperfect datasets you trust, a careful scientist keeps one hand on the brake. This is exactly the pattern you would expect from a real effect slowly emerging. It is also exactly the pattern you would expect from a systematic error hiding in one dataset. The two look alike until more and better data arrive to tell them apart. I want to be honest with you about how much weight this can bear, because the temptation to run ahead of the evidence is strong, and good science resists it. This signal is not a discovery. In the language physicists use, a result at 5 on that significance scale is the threshold for claiming something is real, and a result at 3 is called evidence. Interesting, but not conclusive. The DESI hints sit in that middle territory, provocative, but not proven. More than that, the strength of the signal depends heavily on which supernova catalogue you include, and the catalogue that gives the strongest hint is exactly the one whose possible systematic errors are most debated. There are unknown tensions among the 3 datasets involved, and any of those tensions could be manufacturing an apparent evolution that is not truly there. Several independent teams have looked hard at the same data and concluded that the evidence, while worth taking seriously, does not yet clear the bar, and that the humble constant is still standing. If the evolution is real, the consequences reach far beyond a single adjusted number. A dark energy that changes over time would almost certainly not be Einstein's fixed vacuum energy at all, but something more like a field spread through space, slowly shifting, of the kind theorists have long imagined under the name quintessence. Such a field would have its own dynamics, its own history, perhaps its own connection to the other forces of nature, and it would open a whole landscape of new physics to explore. It might even soften the cosmological constant problem, because a field that evolves toward its present value is a fundamentally different puzzle than a fixed number frozen at an absurdly fine-tuned setting. In one stroke, a confirmed evolution would turn dark energy from a featureless mystery into a thing with moving parts, a thing that could be modeled, predicted, and eventually understood. That is why the DESI hints, faint as they are, have set the field humming. They are not just a tweak to a parameter. They are a possible door into the physics beyond our standard picture. So the honest summary is a strange and thrilling one. After a quarter century in which dark energy sat still and refused to explain itself, we built a machine precise enough to pin it down at last, and the moment we did, it began, faintly, to move. Perhaps the movement is real, and dark energy is dynamic, which would crack open the whole theoretical landscape and might even ease the cosmological constant problem, since a changing field is a very different beast from a fixed vacuum energy. Or perhaps the movement is a mirage in the data, a subtle error that will vanish as the measurements improve over the coming years. We do not yet know, but notice what has happened to our mystery. We came looking for an answer, and instead the question deepened. The largest unknown in physics may have just revealed that it is even less settled than we feared, and the next few years of data will tell us whether we are watching a measurement error or watching the vacuum itself change its mind. Either way, the fate of everything hangs on which it turns out to be. And it truly is the fate of everything, because the value and the behavior of dark energy do not merely describe a distant cosmic curiosity. They decide, quite literally, how the universe ends, and whether it ends at all. That is where we must go next. Everything we have discussed comes to rest on a single question, and it is the most personal question in all of cosmology, even though its answer lies unimaginably far in the future. The question is simply this: how does it all end? And the answer depends entirely on the nature of the thing we cannot explain. Dark energy does not merely fill the universe and push it apart. It writes the final chapter. Depending on what it is, the cosmos faces one of three utterly different fates, and which one awaits everything that exists comes down to the value and the behavior of a number we have spent this whole night failing to understand. Consider first the most likely scenario, the one that follows if dark energy is a true and eternal cosmological constant. In that case, the future is a long, slow, quiet emptying out. The expansion of space will continue to accelerate, forever, with nothing to stop it. One by one, the galaxies beyond our own local neighborhood will be carried away from us, their light stretched to ever longer and redder wavelengths as the space between us swells, until at last each of them crosses that cosmic horizon we spoke of, and its light can never again reach us. This is not a sudden event. It is a gradual fading, a cosmic sunset that lasts billions of years, but it is relentless, and its endpoint is fixed. In roughly 100 to 150 billion years, every galaxy outside our own gravitationally bound group will have slipped beyond the horizon and vanished from view. I want to dwell on what that actually means, because it holds a specific and haunting consequence that is easy to miss. Our own galaxy and its close companions are bound together by gravity, tightly enough that the expansion cannot tear them apart. The Milky Way and its great neighbor Andromeda are already falling toward each other and will merge, some 4 or 5 billion years from now, into a single enormous galaxy, regardless of what dark energy does. That merged island of stars, and the handful of small galaxies bound with it, will remain. But beyond it, in every direction, the universe will empty. The countless other galaxies, the structure that fills the sky today, will all be gone, carried past the horizon, their light lost forever. Let me take you there for a moment, to that far future, because it is a place worth standing in. Imagine a world, tens or 100 billion years from now, orbiting a dim and long-lived red star somewhere in that merged remnant of our galaxy. Imagine, on that world, a curious mind, an astronomer of some kind, gazing upward on a clear night. What do they see? They see stars, the stars of their own galaxy, wheeling overhead, as stars have always done. But beyond those stars, there is nothing, no other galaxies, no faint smudges of distant light, no structure in the dark at all, only an unbroken blackness stretching in every direction, perfect and absolute. And here is the cruelty of it. That astronomer, no matter how brilliant, no matter how fine their instruments, has no way to discover the truth. There are no distant galaxies left to reveal that the universe is expanding. The afterglow of the Big Bang has been stretched and diluted until it is undetectable. Every piece of evidence that would let them reconstruct the history of the cosmos, the expansion, the beginning, the whole grand story we have pieced together, has been carried away by the very expansion it describes. Looking out at their empty sky, they would conclude, reasonably and carefully and completely wrongly, that their galaxy is an eternal island, alone in a static void, the whole of creation. The truth will be gone, not destroyed but removed, pushed beyond reach by the same force that shaped everything. This is not a poetic flourish. It is a careful conclusion, worked out in detail by physicists, who asked what a scientist in the far future could and could not learn. They found that essentially every pillar of modern cosmology, the receding galaxies, the afterglow of the beginning, the abundance of the light elements forged in the first minutes, would be gone or undetectable to observers living after the sky has emptied. The universe does not merely change over time. It edits its own record, and the edits are permanent. A civilization that arises too late is not simply ignorant. It is deceived, presented with a cosmos that appears eternal and static precisely because the evidence of change has been swept beyond the horizon. And the emptying does not stop at the galaxies. Follow the timeline further, and the lights themselves go out. Star formation slows and ceases as the gas runs low. The existing stars burn down, the brightest first, then the long-lived red dwarfs over trillions of years, until the last of them gutters out and the merged galaxy goes dark. What remains is a slowly cooling collection of dead stars, black holes, and cold debris, drifting in an accelerating emptiness, growing colder and more isolated with every passing eon. In the very far future, even the atoms may decay, and the black holes themselves slowly evaporate over spans of time, so long they make the current age of the universe look like a single heartbeat. The end state of a cosmological constant universe is not a bang of any kind. It is a cold, thin, silent, near nothing, expanding forever, approaching but never quite reaching a temperature of absolute zero, a stillness so complete that nothing can ever happen in it again. Sit with that, because it is the deepest strangeness in this whole night, deeper even than the numbers. Cosmic knowledge has an expiration date. We are not living at some arbitrary moment in the history of the universe. We are living in the narrow window when the whole story is still legible in the sky, when the galaxies are still visible, when the afterglow can still be measured, when a species that learns to build telescopes can still read the history of everything in the light around it. That window is closing. Future minds, however wise, will be born into a universe that lies to them by omission, that has quietly erased the evidence of its own origin. Turn that thought over once more, and it becomes almost tender. Of all the moments in the entire life of the universe, from its fiery birth to its cold and endless dwindling, we exist in the brief chapter when it is possible to look up and understand where you are. The galaxies are still there to be seen. The light of the beginning still washes faintly over every antenna we point at the sky. A creature that learns patience and mathematics can, right now, in this cosmic afternoon, reconstruct the whole arc of everything, from the first instant to the final fate. That will not always be possible. It is a gift of timing, and it will expire. There is a strange privilege in being conscious during the age when the universe is still willing to explain itself, and a strange loneliness in knowing that the explanation is being slowly withdrawn. We are the fortunate ones, the readers who arrived while the pages could still be turned. We happen to be here while the book is still open, and the thing that is closing it, page by page, is dark energy. That is one ending. There is a second, and it is far more violent, and it follows if dark energy is not constant but grows stronger with time, the phantom energy we glimpsed in the Deci hints. If the repulsion of the vacuum intensifies without limit, then the acceleration does not merely continue, it runs away. The cosmic horizon draws inward, closer and closer, and the tearing force of the expansion begins to overwhelm not just the space between galaxies, but the bonds within them. First, the galaxy clusters are pulled apart, then individual galaxies, their stars scattered. Then, in the final stages, solar systems are unbound, planets torn from their stars. And at the very end, in the last fraction of a second, the expansion grows so violent that it rips apart planets, then rock, then molecules, then atoms themselves, down to the smallest scales, until the fabric of space is expanding infinitely fast, and nothing bound can survive. Physicists call this the Big Rip, and in the simplest phantom models it arrives in a finite time, perhaps 20 to 50 billion years from now. The sequence has an almost clockwork horror to it, because you can lay out its timeline. In the last 100 million years before the end, galaxy clusters come apart. In the final 60 million years or so, our own galaxy is unbound, its stars flung loose. In the last few months, planetary systems are stripped, worlds torn from their suns. In the final minutes, planets themselves are pulled to pieces, and in the very last fraction of a second, atoms are ripped apart, and then the nuclei within them, as the expansion becomes infinitely fast, and the fabric of space tears through everything that had ever held together. It is not a fading, but a shattering, the universe undone from the largest structures to the smallest, in a cascading tear that accelerates to its own violent finish. Whether this is our fate depends on whether dark energy is truly strengthening, which is exactly the possibility the newest measurements have raised and cannot yet confirm. And there is a third possibility, gentler in one sense and stranger in another. If the Deci hints point the right way, and dark energy is weakening, easing off over cosmic time, then the acceleration might one day stall. Should the repulsion fade far enough, gravity could reassert itself, and the expansion could slow, halt, and reverse, drawing the universe back together over unimaginable spans of time toward a final collapse, a big crunch, everything falling back into the fire it came from. This is the least likely of the three on current evidence, but it is not impossible, and it hangs on the same unknown: a freeze, a rip, or a crunch. Three endings as different as any three things could be, and the universe will choose among them according to the behavior of a number our finest physics gets wrong by 120 orders of magnitude. Notice that all three of these endings, so wildly different in character, hang on the same slender thread. A freeze needs dark energy to stay constant. A rip needs it to strengthen. A crunch needs it to weaken and reverse. The entire branching future of the cosmos, every possible destiny of every star and world and mind that will ever exist, is controlled by the behavior of a single faint energy in the vacuum, the same energy our finest theory cannot explain, and our newest instruments cannot yet pin down. We are in the position of readers who have been handed a story whose ending is written in a language we have only half learned. We can see that there is an ending. We can even list the possibilities. We simply cannot yet read which one it is. This is why dark energy is not an abstraction, not a distant technicality for specialists. It is the author of the last page. Whatever it is, it will decide whether everything that exists fades slowly into cold darkness, or is torn apart in a final violent instant, or collapses back into a single point. We do not get to know which. We only know that the deciding is being done, silently, in the emptiness all around us, by something we cannot name. And perhaps that is the quietest part of the whole disturbance. There is no drama to it. no visible sign, no moment you could point to. The most consequential thing in the universe is doing its work in perfect stillness, in the dark spaces between everything, on a timescale so slow that a human life, a human civilization, the whole span of human history, is far too brief to notice a single step of it. It is happening now, in this room, tonight, and it will still be happening long after the last question about it has been asked. Faced with a mystery this deep, physicists have not simply thrown up their hands. They have proposed a range of possible escapes, serious attempts to explain what dark energy is and why it has the value it does. None has been confirmed. Each trades one discomfort for another, but it is worth walking through them, because the shape of the proposed answers tells you just how strange the question really is. The first escape is the one we have mostly assumed so far, and it is the simplest. Dark energy is exactly what it appears to be: the fixed energy of the vacuum, the cosmological constant, and the enormous disagreement with quantum theory is a sign that we are missing something about how the vacuum energy connects to gravity. In this view, the problem is real, but the constant is genuine, and the resolution will come from a deeper theory, perhaps a theory of quantum gravity, that explains why the vacuum energy is so small. The trouble is that after decades of effort, no such theory has produced a convincing explanation. The simplest answer leaves the central puzzle exactly as sharp as before. The second escape is quintessence, the idea we met earlier. Rather than a fixed constant, dark energy might be a dynamical field spread through all of space, slowly evolving, capable of changing its strength over cosmic time. Quintessence is appealing, precisely because it could explain the faint hints of evolution in the newest data, and because a field that rolls toward its present value feels less arbitrary than a number frozen at an absurdly fine-tuned setting. The cost is that quintessence requires inventing a new field of nature, one so extraordinarily light and so weakly interacting that it has escaped every other detection, and it does not by itself explain why the vacuum energy of all the known fields does not simply swamp it. It moves the mystery rather than removing it. The third escape is bolder. Perhaps there is no dark energy at all, and what we are seeing is a failure of gravity itself. General relativity has been tested exquisitely within the solar system and around dense objects, but the acceleration of the universe is a phenomenon on a scale 1,000 times larger than any of those tests. Maybe, on the largest scales, gravity behaves differently than Einstein's theory says, and what looks like a mysterious repulsive energy is really a correction to the law of gravity. These modified gravity theories are ingenious, but they are tightly constrained. In 2017, astronomers detected gravitational waves and light arriving together from the collision of two neutron stars, having traveled side by side for 130 million years and arriving within about a second of each other. That near-perfect agreement ruled out large families of modified gravity models at a stroke, because many of them predicted that gravity and light should travel at measurably different speeds. The idea is not dead, but the room it has to live in has grown very small. The fourth escape is the most radical and the most unsettling to contemplate, because it changes what kind of question we are even asking. It is the idea of the multiverse. Suppose our universe is one of an enormous, perhaps infinite, collection of universes, each with its own value of the vacuum energy, scattered across every possibility. In most of them, the vacuum energy is large, as our theory predicts, and those universes tear themselves apart or never form structure, sterile and empty. In a rare few, by pure chance, the vacuum energy is tiny, small enough to permit galaxies and stars and observers. And of course we find ourselves in one of those rare few because we could not exist anywhere else. This is the reasoning behind Steven Weinberg's successful prediction that we met earlier, and it has a certain cold logic. It explains the fine-tuning without any fine-tuner. by appeal to an immense lottery of universes in which every ticket is played, and we necessarily hold a winning one. The trouble is obvious. We cannot see these other universes. We may never be able to test whether they exist. And to many physicists, explaining the value of dark energy by saying that it is one draw from an unobservable multitude feels less like an answer and more like a surrender, an admission that the number has no deeper reason at all. There is a fifth escape, quieter than the others, and favored by only a minority of cosmologists, but worth hearing because it is the most deflationary of all. It suggests that dark energy does not exist even as a modification of gravity, and that the apparent acceleration is a kind of illusion produced by the lumpiness of the real universe. The standard analysis assumes, for simplicity, that matter is spread smoothly through space. But the actual cosmos is not smooth. It is a web of dense galaxy clusters, threaded between enormous, nearly empty voids. Time itself, according to general relativity, runs at slightly different rates in dense regions and empty ones, and light takes its path preferentially through the voids. Some physicists argue that when you properly average Einstein's equations over this clumpy reality, you can produce an apparent acceleration without any new energy at all, purely as an artifact of the unevenness. This idea, sometimes called back reaction or the timescape model, is a genuine scientific position, not a fringe rejection of the data. Most cosmologists think the effect is far too small to explain what we see, and so far the standard picture with dark energy fits the observations better. But the proposal is being tested against the same maps and surveys as everything else, and it is a useful reminder that even the existence of dark energy, not just its nature, is something the honest scientist holds open to question. It is worth pausing on how healthy that openness is, because it is exactly the opposite of the caricature in which scientists cling stubbornly to a broken theory. The people who study dark energy are, as a group, its harshest critics. They question whether it is constant. They question whether it evolves. They question whether it is a substance or a failure of gravity. They question whether it exists at all. Every one of these possibilities has serious researchers working to prove it, and the disagreements are aired openly in the same journals. That is not a field in crisis. It is a field doing exactly what it should, in the presence of a genuine unknown, refusing to pretend to a certainty it has not earned. Look at these four escapes, side by side, and a pattern emerges. Each one asks you to accept something profoundly uncomfortable. The vacuum has an energy no theory can compute, or a new invisible field fills all of space, or gravity itself, Einstein's masterpiece, is subtly wrong on the largest scales, or reality is an endless multitude of universes, and ours is simply one of the habitable accidents. There is no gentle option on the menu. Every serious attempt to explain dark energy requires overturning something we thought we understood, and the universe is under no obligation to have chosen the comfortable answer. Perhaps none of these is right, and the true explanation is something no one has yet imagined. That would not be surprising. The honest position, the one the best physicists hold, is that we do not know, and we say it not with frustration, but with a kind of wonder, because a mystery this large is also an invitation. Somewhere in the gap between our theories and this faint, patient energy, there is a piece of physics we have not yet discovered, waiting. We began the night with a promise, a question left hanging in the dark. I told you that of all the unsolved problems in physics, of all the mysteries we could sit with, dark energy is the one that most deserves to be called disturbing, and I asked you to let me earn that word before the night was over. We have walked a long way together since then, through exploding stars and expanding space, through Einstein's blunder and the seething vacuum, through a number wrong by 120 zeros, and a future that empties into darkness. Now, gently, let me gather it all and show you why the word fits. It comes down to three facts, and it is not any one of them that unsettles. It is that they are all true at once. The first fact is that dark energy is real, and it is most of everything. This is not speculation. 3 independent lines of evidence: the dying stars, the afterglow of the beginning, the arrangement of the galaxies, all point to the same conclusion, and we have measured it to a fraction of a percent. 68% of everything, and we cannot name it. That phrase has followed us all night, and by now it should sit differently than it did at the start. It is not a distant curiosity. It is the largest part of the reality you are lying inside of, the space of the room, the gaps between the stars, the fabric of it all. Think for a moment about how thoroughly this reverses our usual relationship with the cosmos. We are used to the idea that the universe is mostly made of the things we study, that stars and planets and atoms are the main event, and the darkness between them is merely the empty stage on which they perform. Dark energy inverts that entirely. The bright, clumped, familiar matter, everything we have ever pointed a telescope at, is the thin exception. The dark, smooth, patient emptiness is the rule. We are the anomaly, the rare, bright specks in a cosmos whose true substance is the thing we cannot see, cannot bottle, cannot name. To learn about dark energy is to learn that we have spent all of history studying the minority and calling it the world. The second fact is that our finest theory of nature predicts this thing wrong by more than any prediction has ever been wrong about anything. Quantum field theory, the most precisely tested idea humanity has ever produced, the theory that describes the behavior of a particle to 12 decimal places, when asked to compute the energy of empty space, overshoots the true value by a factor of 1, followed by up to 120 zeros. We called it the worst prediction in the history of physics, and that phrase, too, should weigh more now than when we first met it, because it means that on the single largest ingredient of the universe, the crown jewel of modern science does not merely fall a little short. It fails more completely than any theory has ever failed anywhere, while remaining flawless everywhere else. Empty space is not empty, and the energy it holds is the exact place where our deepest knowledge collapses into our deepest ignorance. And the third fact is that the value dark energy actually has is not just small, but exquisitely, impossibly fine-tuned, sitting in the narrow band that allows galaxies and stars and planets and observers to exist at all. Turn the dial even modestly, and the cosmos is sterile, a thin grey nothing with no one in it. Instead, the number lands, against odds that defy any easy accounting, precisely where it must for you to be here, awake, wondering about it. And notice that this third fact and the second one do not comfort each other, they compound. Our theory says the vacuum energy should be enormous, enough to have shredded the cosmos in its first instant. Reality says it is a whisper, gentle enough to permit a universe of galaxies and worlds and minds. The gap between those two statements is the largest error in the history of science, and it happens to be filled by exactly the right amount of restraint to allow your existence. We cannot explain why the energy is so small, and we cannot explain why the small amount it has is so perfectly suited to us, and both of those failures live inside the same faint tension in the empty space around you. There is a fourth thread woven through all of this, and it belongs here at the end because it makes the other three sharper. After a quarter century of the constant sitting perfectly still, refusing to explain itself, we finally built instruments precise enough to catch it in the act, and the moment we looked closely, it stirred. The newest maps of the universe hint, faintly and controversially, that dark energy may not be constant after all, that it may have been stronger in the past and be weakening now, that the very foundation stone we have leaned on all night might itself be shifting. Perhaps the hint is real, and dark energy is alive with a history of its own. Perhaps it is a mirage in imperfect data that will fade as the measurements sharpen. We do not yet know. But consider what that uncertainty does to the mystery. It means that at the exact moment our tools grew good enough to pin down the largest unknown in physics, the unknown grew larger. The question did not close, it opened wider. That is a rare and humbling thing, to reach for an answer and find the question deepening in your hands. Hold those three together and feel why the ground gives way. We understand dark energy well enough to weigh it to 2 decimal places, and badly enough to be wrong about it by more than the number of atoms in the universe. It makes up the majority of reality, and it is the one thing our best physics cannot explain. It sits at the exact meeting point of our 2 greatest theories, general relativity and quantum mechanics, and where they meet, they produce nonsense on a scale beyond all other error. And on the value of this single unexplained number hangs the fate of everything that will ever exist, whether the cosmos fades into cold darkness, or tears itself to shreds, or collapses back into fire. It is the largest thing, the least understood thing, and the most consequential thing, all at once. That is why, of all the mysteries in physics, dark energy is the most disturbing. Not because it threatens us, because it surrounds us, and it decides everything, and no one alive can say what it is. Compare it, for a moment, with the other great puzzles we could have chosen. Quantum mechanics is strange, but it works with perfect precision, and its strangeness lives at scales far smaller than anything we handle. The nature of time is a genuine mystery, but it does not sit as a 120 order of magnitude wound in the middle of our equations. Even dark matter, dark energy's shadowy cousin, is a more comfortable problem, because at least we have plausible candidates for what it might be, particles we can hunt for in shielded detectors far underground. Dark energy has none of these mercies. It is not a small effect, it is the majority of the cosmos. It is not precisely predicted, it is catastrophically mispredicted. It is not something we might soon catch in a laboratory, it reveals itself only across billions of light years. And it does not merely puzzle us, it holds the ending of the universe in its hands. On every axis by which a mystery could be measured in size, in depth, in consequence, and in reach, dark energy is the extreme case. That is not a matter of taste. It is what makes it, quite defensibly, the most disturbing mystery in all of physics. And yet the strangest part, the part I keep returning to, is how silent it all is. There is no roar to dark energy, no flash, no visible sign of the most powerful influence in the universe. It does its work in the dark spaces, patiently, on timescales that dwarf not just a human life, but the whole history of life on Earth. You could live 1,000 lifetimes and never feel a single step of it, and yet it is here, right now, in the emptiness of the room, doing the same thing it does between the galaxies, gently insisting that space grow. The most consequential thing in existence is also the quietest. It asks nothing of you. It simply is, and it simply acts, and it will go on acting long after the last person who ever wondered about it has fallen silent. Hold on to that closeness as you settle in. We tend to imagine the great cosmic dramas as far away, safely beyond the reach of an ordinary evening. But this one is not far away. The mystery is not a distant object you would need a telescope to find. It is the medium you are suspended in, the nothing that turns out to be something, the emptiness that is quietly the fullest thing there is. 68% of everything, and we cannot name it, and it is right here. There is a way of holding this that is not frightening at all, and I want to leave you with it as you drift. The discomfort of not knowing is also the shape of an open door. Every great leap in our understanding of the universe has come from exactly this kind of contradiction. A fact that refused to fit, a number that would not behave, until someone found the hidden assumption that, once released, let everything fall into place. Dark energy may be a door of that kind, standing right in the middle of everything we know, waiting for a mind we have not yet raised to walk through it. We are the fortunate ones, alive in the brief cosmic afternoon when the galaxies are still visible and the whole story is still legible in the sky, when the question can still be asked. Most of the universe is a mystery, and it is not out there at a safe distance. It is the ground you rest on and the space you move through, quietly getting larger, even now, even here, in the dark around you. Thank you for spending this time with me, wandering slowly through the strangest and largest question in physics. If this kind of quiet exploration of the universe is how you like to fall asleep, a like or a subscribe would mean a great deal to me, and it genuinely helps me keep making these. And remember, the next time you look up at a clear night sky, that most of what is out there, and most of what is right here around you, is made of something no one on Earth can yet name, gently pushing the whole universe apart. Good night, and may you never look at empty space the same way again.